right, well, welcome everybody. Thanks for coming. So it's my pleasure to introduce Eddy Chen, who's coming here from the University of California, San Diego. So Eddy is actually a co-PI on the Templeton quantum physics project along with us. He's a philosopher of science with a broad range of interests. And he's going to talk to us today about algorithmic randomness, exchangeability, and the principle. So take it away, Eddy.
Thank you so much, Kelvin, for the introduction and the invitation. Thank you all for being here today. It's great to be back at Chapman. And this program is a wonderful thing. It's a dream audience for this paper, because the paper is about some mathematics, some philosophy, and some physics. So at many
Here we are.
Here we go.
All philosophy, all mathematics, and all physics.
All mathematics and all physics.
I'm joking, of course.
So as we discussed a little bit earlier in the seminar at 2 o'clock, this is part of a broader project, understanding a new framework for understanding randomness, probability, and laws of nature. And this is joint work with Jeffrey Barrett of UC Irvine, who is here today too. It's a second paper or project right down for reference. In the first paper, it's about we call L-star laws, a new way of thinking about probability and probabilistic laws in terms of much loved randomness. And this paper is adding to this one something else called exchangeability. Excellent. That tends to be very natural together with L-star law, but also delivers something called the principle, the connection between credences, what's in my mind, and chances, what's in the world. And the third project we hope to carry on in the future is to connect this project to quantum mechanics and maybe statistical mechanics. Maybe both quantum and statistical mechanics. So that is still work in progress. So today we'll talk about this one, introduce this one for back. Okay. The concept of probability has many aspects related to beliefs and credences, related to the world, chances, frequencies, symmetries. Our focus in the project is on probabilistic laws of nature, those laws that involve probabilities in their various statements. Think about probabilistic laws in quantum mechanics and statistical mechanics. Now, those probabilities are objective, often called chances, something that don't depend on our mind or beliefs or ignorance. In previous work, we have developed a new concept of objective probability and thereby a new approach to probabilistic laws. The key is algorithmic randomness, in particular, quantum law of randomness. But there is still an open question. It's actually a long-standing open question that was left open in the first project, but also it's open on almost all approaches to probability. Why should subjective credence, what's in my head, match objective probability, what's in the world? The world has chances, frequencies, patterns of probabilities, but rational agents have credences, degrees of belief. The probability axioms, the Kolmogorov axis, for example, they don't connect the two. You can be coherent probabilistically and hold credences that don't match the chances. Why should chance constrain credence in a particular way? And this, we were discussing terminology in the discussion earlier, which is the difference between notions of probability, such as credence, chance, frequency. They can all be called probabilities, but this is subjective. These two are objective. The frequency, say, of heads in a row of many, many tosses is obviously objective and in the world, but chances themselves, a little bit hard to interpret, right? There are different interpretations of chances. So it's pretty much open. What exactly is foundation of chance? Okay. There is a reasonable principle called the principal principle that seems to capture all we know or much of what we know about chance. Even without saying what chance is, it seems to have certain roles to play in our conceptual scheme. And here's a rough statement given by David Lewis. If the chance of some event is X, say rain tomorrow, or Quillen had something, right, is 0.5, and evidence K is admissible. It's not about the outcome tomorrow. It's not about oracle or crystal ball. Then the credence A, conditional on K and chance of A equals X, should be X, or equals to X. So the PP captures much of what we know about chance. On the right, statistical inference and scientific prediction. And it seems a reasonable rule to endorse, but it is very hard to prove. I mean, one of the complications is that this is not the only version of the chance and credence norm in the literature. There are other norms, the new principle, for example, generalized principle, all of them are competing against each other. So we managed to know why this is true and in which version it is true. So in this paper, we introduce a general framework uniting algorithmic randomness with exchangeable priors. And that's the other assumption in this framework. The motivation to bring together various ideas, often discussed in isolation, to address foundational issues in philosophy probability. And one of the payoffs is that the principle naturally emerges as a theorem in the framework. We provide what appears to be the first derivation of principle that avoids circularity issues. The success of this derivation suggests the framework captures something fundamental about chance, credence, and laws of nature. Maybe introduction to. So I think it's kind of an attractive theoretical package of different ideas, and this might be evidence of the broader potential for illuminating other issues about probabilities. Okay. So let me now give you some background on the Aristotle framework before going to exchangeability. Probabilistic laws, as they're usually understood, involve a variety of determination. A simple example. Think about a coin toss example. We have a coin, tosses many, many times. It produces, in the limit, an infinite omega sequence of results, R1, R2, R3, forever. Now, each possible binary sequence of 0 ones describes a possible world, possible way the world could be, the simple world, toy model world, right? Now, let omega L be the set of all such worlds that accord with the law L, that are compatible with the law L. What is the law L again? Think about following simple law of L. Think about a Bernoulli ID 0.5 kind of law. Each element in the omega sequence of coin tosses, R1, R2, is determined independently and with unbiased probability of heads and tails. You expect, for example, the sequence to be something like this: 1, 0, 1, 1, 0, 0. Of course, it's compatible with other sequences, say all ones, all zeros, alternating 1, 0, 1, zeros, all of them compatible. Each toss outcome has probability 0.5, and each toss is independent of other tosses. One might think of L as describing a fundamentally random process, something like starting with a sequence of spin-half particles in quantum mechanics, each in eigenstate of z spin, right? So z spin, z spin, z spin, z spin, and then measuring their x spins in turn. So quantum mechanically, the probability is 50-50 for each one, independent. Now, as probabilistic laws are typically understood, omega L is a set of all omega sequences. All the 0 1 sequences in counter space. L does not rule out any world. Even this one, all zeros. Even this one, all ones, are allowed by L. So L is compatible with all of them. And many more. A world compatible with L might exhibit any frequency or no limit frequency at all. In all heads world, a world with 1/3 heads. Even the full history of a world will fully determine L in a continuous cardinality of cases. There's even many such maverick worlds that don't look for the right pattern for L, but still compatible with law L. Even the whole set of binary sequences does not determine L over any other probabilistic law. Because any such law, say Bernoulli 0.5, Bernoulli 0.6, Bernoulli 0.7 biases, they're all compatible with the same set of binding sequences, namely all of them, the entire counter space. So they are very permissive and they're compatible with the same set of models, same set of sequences. So this shows it may be impossible to learn if a law is true with even complete evidence. Of course, we human beings in the labs have much less evidence than complete evidence with infinite limit. But even with complete evidence, it may be impossible to learn that the law of L is true for this one, for this one, for this one, which is a governing law. There's no way to learn, even with complete evidence. There are omega sequences that might occur but provide no evidence, empirical evidence whatsoever for accepting L. Okay. In the words like all heads or tails, or whatever.
It's not like.
Sorry?
Sure that there are no evidence because you have a continuous number of sequences and only a numeral number of evidences. So certainly there are some ones that there are no evidence.
That's true too. That's true too. By the way, clarification questions, feel free to ask them during the talk. In such worlds, one would never have any empirical support for accepting the correct probabilistic law, even with full evidence. There are infinite many such worlds. Now, in previous work, we suggest we can get a tighter fit between probabilistic laws and empirical evidence. The proposal is to systematically replace L laws with something called L star. They are, in a sense, logically stronger than L laws. A schematic form of L star law looks like this. The omega sequence of coin tosses, the actual sequence, is random with unbiased random frequencies of heads and tails. If it is a law, then any physically possible sequence must be random by some definition of randomness, respect to some frequencies. Here being random is a property of the entire omega sequence. It's called outcome randomness. It's agnostic about the process generating the outcome. If I give you the sequence, the property can tell me whether it's random or not. So it's kind of an outcome randomness. The notion should be defined. The notions of randomness considered here are algorithmic. That's why we call algorithmic randomness being crucial here. Defined in terms of statistical tests to determine whether an omega sequence exhibits any specifiable pattern. Each sequence can either pass or fail particular tests for being random. Here's a visual example. So think about L, omega L, as a bigger square. And that's the entire counter space. L star, omega L star, is a proper subset of omega L. So omega L star, instead of all were compatible with L star, all of them exhibit random, unbiased sequences stipulated by L star. So this sequence, all ones, this sequence, all zeros, and similarly 1, 0, 1, 0, 1, 0, they are not in omega L star, but in the complement of omega L star in omega L, in the refuge. The refuge actually too large here. Actually, cannot even see them because they're measured 0 by the light of L. In other words, omega L star contains no maverick worlds. The deviant histories world, the non-random pattern world. The maverick worlds are those that exhibit some simple pattern, or fail to exhibit the right frequencies, or fail to have any limiting frequency at all. Now, if L star is true, then any physically possible world fully determines L star. Any inquiry in any physically possible world will determine the truth of L star by considering the results of our coin tosses. With complete evidence, when we're surely learning up to an equivalence class of computationally indistinguishable laws. And I'm not going to expand on the proviso here in this talk, but just kind of briefly, if you have more than Turing string computation, you can tell them apart by some evidence. Okay, the probabilistic law, like L star, is much like deterministic law in this way. So the plan for this talk is first to clarify definition of randomness or L star law, how it rules out most worlds, And L-star leads to a natural question. How does a law about infinite sequences, it's all infinite sequences, how does a law about infinite sequences relate to my credences about upcoming observations in the finite short run? Say, rain tomorrow, pause for the next one. We show that if you assume a version of what David Keming calls exchangeability, which is a natural inductive hypothesis of uniformity of nature, accepting L-star law entails accepting a version of the principal principle, which is a precise answer to the previous question. That is, your credences about the next round and finite short run has to match the objective probabilities given by L-star law, given the assumption of probability. Okay, let's first define the randomness constraint. This is the part I left out in my discussion in the previous session. So what does L-star law mean? What is my law of randomness? We need a test of randomness for omega sequences such that those sequences are ruled out and this sequence is ruled in. A random sequence tosses with an unbiased coin to exhibit even random frequency heads and tails per limit, 50-50 heads and tails per limit. But it's not sufficient. So for example, we have 1, 0, 1, 0, 1, 0 that has the right frequency, 50-50, but not random. There are 3 further conditions for unbiased random sequence: patternless, generic or typical, and not allowing for such a fair variance strategy. Let's start with the first condition. The non-omega sequence is random only if it exhibits no finite satisfiable regularity. Algorithmic tests are particularly helpful characterizing patternless without patterns, no simple regularity. So here's the first path. It's not going to work, but let's try. The non-omega sequence is patternless, hence random, even only if there's no finite length algorithm, say, something you can write down in a piece of paper that produces a sequence. A finite length algorithm that can express a regularity is something like that one might even think of as a deterministic law. So for this one, you can say repeat 1, 0 forever. A very simple algorithm. You can do it. That's not random. But is that sufficient? It is not. Here's a counterexample. Think about a 3-block pattern that's repeated forever of 1,000 heads, 1,000 tails, followed by 1,000 heads and tails unbiased random mixtures. So you have 1,000 heads, all head sequence, 1,000 tails, all 0 sequence, 1,000, followed by 1,000 random looking heads, tails, and repeat this. The rate frequency heads and tails in the full sequence is unbiased, and moreover, sequence cannot be compressed by finite length algorithm, because there's always a 3rd block, 6th block, 9th block, and so on that cannot be compressed unless by brute force. But the sequence is not random. We can design a gambling strategy and enjoy unbounded wealth, right? You can bet all heads for the first 1,000, bet again for the second 1,000, and don't bet, so you don't lose money. Bet again, and don't bet. In this way, your capital will increase forever. You gain lots of money. So by this definition of gambling strategy, it is not random. The problem is there is no bound on the amount of financial segments of the sequence can be compressed. If you go further and further and further in the sequence, you can always compress by more and more and more. There's no bound on how much the sequence can be compressed. One might even write a short program, take advantage of the regularity. One can eventually shorten the representation of the intersegments by any constant C. And this observation provides a key idea behind Kolmogorov charting randomness. Definition here. So let's say an omega sequence Kolmogorov charting random, if and only if there's a constant C such that all finite intersegments are C compressible by a prefix-free Turing machine. By the way, definitions are in the handout and first page. Initial segment is C compressible just in case it is not represented by an algorithm that is shorter than the initial segment. And a prefix-free Turing machine is something like a Turing machine that knows when to stop reading these like top phone numbers at fixed length, so you know when you have dialed enough digits. And this can deal with the 3-block pattern. because this one, there's no upper bound of how much can shorten the description. Okay. Second condition, being generic and typical. So randomness as typicality, here's the first half condition. A non-good sequence X is random if and only if it satisfies all typicality problems. It is too strong. Being different from X itself is a property held by almost all, or measure one, sequences. The first half condition implies that no on-good sequence is ever random. So we have to restrict the class of typicality properties to some special properties. And that was a hard problem until 1966 when Martin solved it. He offered a remarkably simple satisfactory solution in terms of computable functions and effective computation. So Martin randomness is defined as follows. A non-good sequence is Martin random if and only it belongs to every effective two-measure set, measure one set. That is, belongs to no effective measure zero set. Not just measure one, measure zero, but effective measure zero, effective measure. Or effective in terms of computational program. So let's say a set E in the counter space of possible binary sequences is effective measure zero, just in case this uniformly effective sequence open sets G1, G2, such that all n E is contained in Gn, and the mu of Gn is getting smaller and smaller and smaller. And moreover, this entire sequence of open sets can be determined by a single program. It's called uniformly effective program. And this can deal with this example too. Because you can imagine cylinder sets describing just the first two blocks, just the first five blocks, and so on, that contain fewer sequences, and also contain this particular sequence. You can define a particular algorithm to generate a whole sequence of open sets. So again, by definition, this is ruled out as non-random. Surprisingly, the two different definitions of randomness are equivalent. By Schnorr theorem, an on-good sequence is multi-log random, think about typicality randomness, if and only if it is homogeneity random. There's no pattern randomness, right? Patternlessness and typicality are two sides of the same coin. Moreover, they're also equivalent to the betting criterion. That is, no computably enumerable martingale succeeds on the on-good sequence. So all three definitions are actually sides of the same coin. I guess it's not a coin. It's going to be some three-sided thing. Upshot is that multi-log randomness is simple and natural, and very surprisingly, it is equivalent to similarly different characterizations of randomness. Just like there's Church-Turing thesis for, what is the definition for computable function? The Church-Turing definition, the two sides of the same thing, they're equivalent, surprisingly. Multi-log training thesis says multi-log randomness is the right definition of randomness. We don't need something so strong here, but just to motivate. That is, they're natural to consider multi-log randomness as definition for a random sequence or random history. So for this reasons, we're going to use multi-log randomness to specify the law L star as a constraint on a set of physically powerful worlds. There are other choices. You can use Schnorr randomness too. We're going to use multi-log randomness for concreteness here. So L star means L star ML. The omega sequence of coin tosses is multi-log random with unbivalent frequency pairs and tails. Here, all of the worlds committed by omega L star are random with well-defined frequencies. Now, just to emphasize, this is the simplest version of L star. Corresponds to L star 0.5 million frequency pairs. There's also kind of a measure here. So you think about omega L star defined with some beta 0.5 measure. This is the reference measure for randomness. The nomic measure. The law carries with it this measure. Now, if you change this to beta 0.6, you're going to get a different set of sequences that are random, disjoint set from L star 0.5. Change to 0.7, 0.8, 0.9, you get different sets. And the different biases, given bias randomness too. Actually, for any computable measure, you can generate definition of Markov randomness for that measure need. So it's quite general in this way. But I'm going to stick with beta 0.5 for concreteness and for simplicity. homework. You can carry out generalization yourself. These other measures. Okay. Now, why consider L star law and what difference does it make? First of all, empirical coherence is guaranteed. With L star, it is always possible, if you have complete evidence, to determine the true law from just observations. And second, L star is empirically equivalent to standard L law if you are strictly to two-instance computation. So two computable agents cannot tell whether L star is true or L law is true based on observations alone. We need some theoretical arguments that we like L star, maybe you like L. But in any case, it's empirically equivalent up to two-instance computation. Furthermore, L star clarifies typicality. It entails an effective version of what's called the probabilistic principle, which I won't explain in this talk. One metaphysics of chance and laws of nature is called humanism. Something called the big bad bug, a scary thing is dead. But there's no need to define fit either. So a bunch of puzzles for the metaphysics of laws and chance become or even arise here. A non-humanism, in particular version of laws as constraints that Emily and I both like. Probabilistic laws can be understood as constraint laws that really rule out some histories, because L laws don't rule out any histories. They're compatible with the entire common space. But L star laws, they have disjoint supports. They rule out histories. They are non-random according to the measure you carry with them. So in short, it solves many conceptual puzzles about probability. Okay, and that was basically a summary of the first paper. This coming out in yes. And arXiv 2. Let's get to the part of the second paper, which is the new result, which I usually share here too. With L star law, the infinite sequence must have a precise long-run pattern in the infinite limit. Now imagine limits are pretty far away things, and tails of the infinite limits quite far away. Nothing finite sequences are constrained by the tail, right? So with this infinite limit and long-run pattern of randomness and frequency constraint, we obtain a new notion of probability and new notion of probabilistic laws. It's very nice for theoretical reasons, but there's still a lingering problem. It is the same problem we discussed earlier about principle. And in this particular context, one might be wondering, the long run is a misleading guide to the current affairs, because in the long run, we are all dead. This is a quote from Keynes. And I think he was thinking about long run patterns in economics something, but I think it applies here too, right? And this is something that people have raised over and over again about the L star law framework, but you can raise this for any theories that rely on infinite limits. Because we're finding creatures, we live so many years and we're God. So how does the infinite law of infinite constraint help us in the here and now? How to go from infinite patterns guaranteed by L star to short run or even single shot credences about upcoming observations? The next talks. Tomorrow's better. For example, if the limiting frequency of hat is, say, theta equals 0.5 in an infinite limit, then for any upcoming trial, maybe it's reasonable that we should assign credence 0.5 to heads. And yet, there's no connection logically or probabilistically. The laws of probability don't guarantee this connection. Explaining why this is rational is justify a principle. Knowing the chance or some objective probabilities is theta entails that a credence must be theta. It turns out that, this is a problem for both L law and L star laws, but it turns out that L star laws have a unique advantage here of answering this question. In fact, under certain assumptions, L star laws entail principal, as we shall show. Now, the principle, again, is traditionally formulated as a link between the agent's credence and the event's objective probabilities. So let CR be the agent's credence function, and let CH be the chance function. PP then imposes a precise rational requirement. For any event A, here think about Borel's sigma algebra, for some kind of magical space, the event A is a magical event. The credence of A conditional on chance A equals X equals X. So if you know the chance of coin landing heads is 0.5, then the credence that you will land heads is 0.5, or should be 0.5. That's what the principle demands. Seems reasonable, seems motivated. Moreover, this credence should be resilient in some sense. For any proposition K that's admissible, think about the result of our past tosses, previous histories. Again, conditionalizing further on K, the credence should be invariant, should be the same. You should not shift the credence by conditioning on other facts, but other tosses. So conditioning on the previous toss, the credence that will be when has still 0.5. Okay. And that seems to be the role of chance in our credence rationality. Now, more generally, one deposits a general probabilistic law L that determines the probability measure mu L over the space of complete world histories. This is motivated by considerations of physical theories, in quantum mechanics, statistical mechanics. We don't always assign, or when we first assign a single shot chance for coin and rain and so on, we assign some law of nature about the whole, patterns, general behaviors, and derive those single shot chances sometimes from laws. Think about event like rain or coin landing heads as macroscopic post-grain histories of the elementary particles, elementary events. So in this way, L will assign some measure, mu of L, on the space of complete world history of wave functions, particle histories, on phase space or something, and then you can derive single shot event probabilities from this measure mu. So this motivates a more general formulation of PP that directly connects the no-link measure, the measure of the law, to credence. So for this one, the ID law, the measure is Bernoulli 0.5. For this one, it's Bernoulli 0.6, Bernoulli 0.7. And for this one, it's also Bernoulli 0.5. Okay, so the PP decomposes into two separate principles. One is the law, the credence principle. For any event A, CR of A given L is mu L of A. The conditional credence of A given L equals to how much law measures, or the nomic measure. Resiliency. For any K admissible with respect to A relative to L, then conditionally further on K, you still have the same credence, mu L of A. So in this context, PP is the conjunction of law of credence principle plus resiliency. When made suitably precise, both LCP and resiliency can be proven in L star field when assuming what Definition calls exchangeability. So what exchangeability? Let's start with a simple example. A sequence of coin flips, x1, x2, x3, is exchangeable for some probability function if the order of heads and tails does not matter to the joint probability. Concretely, if you find a sequence that has the same number of heads and tails, doesn't matter the ordering of heads and tails, and they have to have the same probability. And that's exchangeable probability function. So mathematically, a finite or infinite sequence of random variables taking value some set x is exchangeable just in case for every number n, for every combination pi of indices 1 to n, the joint probability of x1 to xn equals to the permuted joint probability of x pi 1 to x pi n. Equivalently, the joint distribution is invariant on all finite permutations of indices. So here's a concrete model, and we see this a lot in different contexts in the medical sciences, physical sciences. You have exchangeable models, even though we don't have IID models all the time. So exchangeable model is more general than IID models. So here's an urn model. Start with an urn containing A red and B blue balls. At each step, draw one ball at random, notice color, return it to the urn along with alpha additional balls of the same color. It's called join with replacement. Observe the color sequence, red, blue, blue, red, and so on, as draws continue. Now, this is exchangeable because over n draws, the probability of seeing exactly R red draws depends only on R, how many red you see, not on order in which reds and blues appear in the sequence. And any two sequences, the same number of reds, draws have the same probability. This invariance makes the sequence exchangeable. Another model you can think about is drawing without replacement. So think about instead of with reinforcement, you take the red one out and split it. Don't put anything back. And the same thing will happen. It will be exchangeable. And that one has a precise name to it. It's called a hypergeometric distribution. Now, David and Eddy proved 100 years ago a remarkable theorem about probability for exchangeability, which is the key result we'll use in our proof of the principal principle. So he didn't prove this particular version, but I'm going to use this in an ahistorical way because it's illuminating for taking the limit. So for the finite version, we can have the following. If P is an exchangeable probability on finite sequences, then there exists distribution mu on 0 to n such that for each sequence x1, xn, the joint probability is exactly a mixture of hypergeometric distributions, namely join with replacement, without replacement. Moreover, the mixing measure mu r here is induced by P. So if P regards, say, r less than or equals to 0.5 is 0.7, then mu has also regard this event with 0.7. So mu just follows P in terms of measure of mu. Now, why this is important is that it turns out if you let the sequence goes longer as n goes larger, the hypergeometrics individually become very close to what's called mononomial distributions, and they're representing the RID distributions, drawing with replacement. Indeed, the error bound can be made precise by this number 4k over n. N is the length of the sequence. K is however many coordinates we're evaluating for the event A. So keeping k fixed and letting n goes larger, error becomes smaller and smaller. In an infinite limit, as n goes to infinity, 4k over n equals to exactly 0. And that's how we arrive at the infinite version, which is what David proved. The infinite version of the theorem says follows. Suppose P is a single probability measure on this counter space on infinite sequences endowed with product sigma algebra, the Borel sigma algebra counter set. Then there exists a unique probability measure mu on 0 to 1 such that the joint probability is exactly a mixture of Bernoulli distributions with biased data. Here, beta theta is different Bernoulli distributions with biased data. Theta equals 0.5 is the unbiased Bernoulli, with 0.9 is the bare biased Bernoulli. Moreover, the mixing measure mu d theta is induced by P, just like this. Yeah.
When you say P is exchangeable on now an infinite sequence, are we counting every single possible permutation of the infinite sequence?
It's like
alter the relative frequency by doing like strange permutations.
So we count this for every n for every finite sequence.
So we're just the initial segments.
Yes.
That's right. Yeah.
It's exchangeable in all initial segments.
For any arbitrary initial segment, however long it takes, and every computation of that, just control. Thus, exchangeability implies P is a mixture of bias core and Bernoulli distributions. And this is a powerful result. By itself does not imply the principle, but it is something to start. So the second component of our framework. Now, why consider exchangeability to begin with? The motivation is induction. In scientific inquiry, we have to rely on certain inductive hypotheses to make inferences from observation to unobserved data. We often rely on a vague principle of uniformity. We say nature is uniform in some sense. Now, a precise version is encoded in one's prior credence as exchangeability, comparing invariance of time indices. Now, what we really want is to believe in the simplicity of physical laws. Doesn't guarantee unconditional exchangeability, but we can still have conditional exchangeability. Conditional on some laws of nature, L star and L, we expect conditional exchangeability to hold. So Moreover, exchangeability embodies several different commitments. For example, just by exchangeability itself, so if CR is exchangeable, then CR HI and equals CR HJ. Marginals agree for all IJ. Moreover, CR, H2, so the XI J, right, equivalent. Moreover, X2 equals to has given X1 is has. It is bigger than or equal to CR of X2 is unconditional. So this suggests there's probabilistic uniformity in credence. And this suggests that past experiences of seeing successes and seeing heads can increase your credence of heads. And moreover, there's a third thing that's, I think, very striking too. An agent within prior must believe, with probability 1, that with repeated observations, the random frequencies will converge in the infinite limit. So there's going to be stable patterns. This is probability 1. So for these reasons, exchangeability really is a precise embodiment for several inductive commitments we take for granted in standard practice. So this is the core assumption in our proof. The second component of framework, which is conditional exchangeability. The conditional credence function given L star, CR given L star, is exchangeable. What is the status of CE itself? Well, if one has the view of a Bayesian who think there is no norms beyond probability calculus, then exchangeability is a rationally permissible subjective norm, subjective principle. It is one legitimate reasonable choice, but not mandated for agents who merely want to remain coherent. It's one view to take. The second view is more objective Bayesian. It says it is a rational requirement for induction. The latter is a hallmark of rationality. The third view is a more moderate view than the second, but maybe stronger than one, which says that C is a precondition for rational empirical inquiry in the probabilistic universe. We need C to get science started by enabling systematic learning from observations. If you have different interpretation of Bayesianism, you have different interpretation of the status of proof. Now, we want to emphasize that exchangeability and L star are compatible. L star requires that infinite sequence multi-log random. And because multi-log randomness is a property of the tail of the infinite sequence, it doesn't actually constrain the finite seconds. So no finite string is excluded from appearing in multi-log random sequence. And thus, L star does not force any finite pattern to have probability 0. And this crucially leaves room for a conditionally exchangeable prior that treats all finite strings symmetrically. Imagine, for example, suppose a version of frequentism that thinks that, well, the frequency of something must be 50-50 in the limit. But also, if you have a million or billion heads in a row, that's not random enough. In that case, this is ruled out. And if you have not this one, but suppose you have a million 1 zeros, even that is not allowed, right? So you have a finite string like this are not allowed. But exchangeability demands that this to be possible because you have the same probability as a random looking finite string. So in that case, this one will not be compatible with exchangeability. So multi-log randomness is natural home for exchangeable prior. It is doesn't this kind of situation will not arise multi-log randomness. Moreover, there's a harmony between the two. If one starts with unbiased exchangeable prior, one will be sure with probability 1 that the sequence is multi-log random. Hence, L star law and exchangeability naturally correlate with each other. However, multi-log random sequence does not imply that we have to treat the sequence in permutation in varying ways doesn't entail exchangeable priors. You can actually have a conditional prior that's non-exchangeable, even anti-inductive. Nothing for probability will imply that this prediction. So it's a separate assumption we have to make in addition to L star. Okay, so our framework now is assembled. We have two components, one L star law and two conditional exchangeable priors. And the two are independent components, don't entail each other, but they're harmonious together because of the various properties of exchangeability and multiple randomness. Now here we're going to use L star for 0.5 measure and exchangeability without additional structures. There's a simple version of the framework, but generalized to other bias measures and less than fully exchangeable priors. Now, once two components are in place, the proof is surprisingly elementary. Any questions for now? Clarification? Okay. So now we are ready to see whether two components entail the principal principle. We can prove that under conditional exchangeability, under conditional exchangeability, CR of L star equals to mu L star of, and this equals to beta 45 measure of these two measures are equivalent. Okay, how do you prove this? First, notice that L star, by definition of multiple randomness, unique to L star, implies beta equals to 0.5. It's the first step. Second step, a definition of exchangeability, CR of this is a probability function that's exchangeable by Definite's theorem. This is exactly a mixture of different Bernoulli data measures of this. I'm going to write A for now, just to def some event A, an arbitrary event. The dot is hard to see. Okay. With a mixing measure, mu of the theta. So it's by definition of L star law, this by definite representation. And moreover, the mu d theta is induced uniquely by this credence function. Again, by the theorem. Okay. Now, so here's a fact about probability theory from the probability axis. If A, if P implies Q, then the probability of Q given P, assuming P has positive probability, equals to 1. So in this case, the mu of d theta equals to 0.5 equals to 1 because CR theta equals to 1.5 given L star equals to 1. And this follows from the first thing, right? L star implies theta equals 0.5, and therefore the credence of theta equals 0.5 given L star is 1. And now, what do we have here? Well, this now becomes not a mixture anymore. But mu is a delta function on theta equals 0.5. And therefore, this is theta 0.5 of A. Because for every other value, mu has exactly 0 probability in interval 2. So this means, just to rewrite it again, CR A given L star equals to beta 0.5 of A, and we're done. Yeah.
I feel like you're assuming a lot with L star that the sequence is Martin-Loeb random, but you're only using that the limited relative frequency is a half. Could you just replace the L star condition with the condition that not at probability 1, like exactly that limiting relative frequency is 1/2?
Good. That's a good question. You can in this proof. But again, there is the worry about exchangeability, right? Exchangeability demands that all finite strings are possible given a fixed frequency. But certain frequencies don't allow that. So it is the harmony between exchangeability and Martin-Loeb randomness that allows the consistency of the framework to be demonstrated. So many versions of frequentism don't allow exchangeability. So we don't use Martin-Loeb randomness in this proof, but is what allows you to sample this as a consistent package. Does it make sense? Okay. So, moreover, it is highly resilient on the conditioning. That is, the credence measure we get equals to the nomic measure. Because nomic measure is ID measure, it is highly resilient. ID implies independence. Being ID Bernoulli theta means each toss xk is independent of other tosses. Learning the outcomes of finite set of other tosses in the universe, excluding xk, does not change your credence about xk. Okay. Call this invariance resiliency. So admissible information cannot shift the credence distribution of xk. More precisely, we define admissibility as follows. K is admissible with respect to event A and L. L star just in case K is screened off from A. I'm a nomic measure beta 0.5 and beta 0.5 of K greater than 0. In summary, an agent whose credence function satisfies condition stability is guaranteed to have credences that match the non-linear frequency preserved by L star law, satisfying resilience. Such an agent has credences that satisfy the principle, and that's the argument that the framework entails the principle. Let's come back to the quote Payne had about in the long run we all dead. So, case 1, infinite universe, true on credences. Question: if the universe is infinite, why should my credence about tomorrow's event match the linear right frequency? Answer: the proof shows that you must match the true on credences to the non-linear frequency. It guarantees resiliency, then if other outcomes won't change tomorrow's probability, assuming exchangeability. And that's what we have shown in the previous proof. Now, one can ask a harder question. If the universe is actually finite, does the infinite sequence proof fail to apply? First answer: our current physical theories do not impose a finite stopping point for the universe. Trajectories in classical mechanics and quantum theory extend to infinity forever. Now, even in the finite world, the finite version of those theorems provide close approximations to the infinite case. In fact, we derive a corollary from previous result as follows. The approximation improves if the world runs long. So you can actually define a finite version of L star law as this. I'm going to be brief here. I'll talk about this more in the Q&A. Suppose the universe has a temporal length of W trials only, and then it ends, right? Only W trials. We shall use beta 0.5 as a reference measure. Again, define a law L star epsilon z for binary strings of length W is the finite length of the universe. It's a conjunction following two constraints. One, the frequency constraint. The right frequency of heads is in the range 0.5 plus minus epsilon. Epsilon is somewhat small compared to W, so it's take the ratio of log W over W, take a square root. The randomness constraint, random z, the string's prefix 3 common complexity relative to some Turing machine M is greater than or equal to this thing, minus log beta 0.5 s minus z equals to W minus z in the case of unbiased Bernoulli process, where z is a number small compared to W that allows some small degree of pattern in the random string. But definitely just let z equals to square root of W. It turns out that we can prove a similar theorem for finite strings, such that an exchangeable credence on finite universes is very close to the Bernoulli 0.5 measure with this error term, 3 error terms. Now, as W grows, all 3 error terms shrink. In the infinite limit, as W goes to infinity, the error is exactly 0. Recovering the exact infinite histories result previously is evidence that the framework is correctly calibrated. It shows that the infinite version is not mere idealization, but a precise and natural limit for the finite case, and in our mind, thus all the more compelling. Now, for Humeans who think that laws are not governing facts, but mere descriptions of what happens in some sophisticated sense, this approach kills the big bad bug. There's no more inconsistency between human supervenience and the principal, and therefore no need for the new principle. It eliminates various problems defining fit, because we can only rely, we don't have to rely on fit in breaking in different systems. For non-Humeans, we think the law is governed by constraining. In this sense, L star are really governed by constraining physical possibilities and rule out some magic worlds. And assuming conditional exchangeability, the global constraint of the infinite universe, or finite universe, also entails rational credences about the finite true or wrong. So for agents with inductive commitments, the agent has to have the nomic measure for finite true or wrong events. For both in the L star universe, we don't need additional analysis of chance or typicality. In comparison to other approaches in literature, just by the principle of Wookham-Schwartz and Pettigrew, their versions suffer from certain kind of worries about circularity. They presuppose some other principles. So Pettigrew assumes the deference principle to chance, and Schwartz assumes the principle of indifference. They look like PP in some context. So for that reason, they might appear circular. Those words don't arise in this version of the proof of principle. Okay, so this is the second step of the project on L star laws that Jeff and I have been working on. And previously we thought about L star just for the metaphysical laws and now connects to the principle and to credences that agents should have. In future work, we'll talk about quantum mechanics and statistical mechanics. But this is already a counterexample to the claim inspired by Lewis and other Humeans who think that justifying the principles is possible or significantly easier only in the Humean frame. And in this case, both metaphysics, L star, and epistemology induction contribute to our proof of the principle. But human supervenience plays no role. Okay, in conclusion, we presented a novel non-circular proof of the principle. The core assumption embodies inductive hypothesis, a conditional belief in uniformity of nature. It establishes directly between long-run patterns and short-run credences. Guessing PP is possible in both Humean and non-Humean frameworks. It's quite neutral about metaphysics. And moreover, I think our framework unites several concepts developed independently across decades in probability theory. Definite exchangeability, like law of randomness, chance-credence norms, and statistical constraining laws. And they show them to be complementary pieces of a single puzzle. And I think that this makes the framework more attractive and worthy of consideration. Okay, thank you for your attention.
If you like.
Thanks. Questions?
Yeah, I mean, I'm sure there's a lot of different proofs of it, but do you happen to know if there's a constructive proof for the Finetti representation here?
You're taking the limit, or
What was that?
there's a limit in the proof. So
Yeah. Is the Bernoulli measure obtained constructed by proof? Because if it's supposed to be epistemically useful for credence, for connecting credence to objective chance, it would seem that the proof of Finetti better be constructed.
oh, interesting.
Because I can see it, I mean, if we're willing to accept, just the mere existence as establishing that there's a genuine notion of objective chance,
Right.
that we can have some kind of confidence in. But in order for that fact to directly participate in the proper, conditioning of credence, we need to be part of that mental context.
That's an interesting question. I'm not aware of any constructed proof of differential theorem in the case.
Or is what I'm saying, does it sound misguided somehow?
I don't think it's misguided. I think it's one condition for epistemically accessible. I think it's one notion. It's not the only notion. I have a kind of liberal notion of epistemic accessible. I think that taking accidental choice, for example, is okay for agents like us. But I know some people are more.
Well, yeah. So I'm saying you can accept that.
Yeah.
Okay, so you don't have. It's not partial to the constructivists to have this concern. I think that the specific way it's being applied here, if I understand how it's being applied, it is making a claim for mental conflict. That Diffinetti's representation theorem itself doesn't mean so you can accept non-constructive proofs all you want, but when it comes to applying one of them, this one potentially to connect with with the justification of our credences.
The final version
supposed to match objective chance with credence.
Yeah.
And have a method for doing it.
Oh, I don't think I need a method for
You
connecting
show
them.
it's somehow
I mean,
justifiable.
yeah, I think for the stronger notion of epistemic accessibility, maybe the finite versions will help. For the infinite version, I'm not aware of any constructed proof. Maybe you know, Joe?
I don't know if the
Yeah.
proof is constructive.
Right.
My intuition would be the same as yours. I think that the practical considerations are best handled under the finite L-star laws. Okay.
Yeah, I still kind of feel like an L-star law is a very big assumption to make. Like, I guess they have measure 1 over vector space, random sequence. But like to actually construct or have a like Martin Loaf random, like they're somewhat complex to construct. They're like real, like it's not nothing to have them. Like you can use them to solve a whole.
Not true.
Right.
Yeah.
To show that a particular sequence.
So I'm not necessarily sure if we can justify them sort of existing physically in like a case of an infinite universe. Like if I flipped a coin, would it really give a Martin Loaf random? Or
What about Bell law? They include automatic law of random sequence and more. They send a Bernoulli kind of independent.
Yeah, but that's a strictly weaker condition.
But in some sense, it's stronger. It has more possible sequences. So either denying or accepting them is metaphysical commitment too, right?
Yeah, so if I believe a standard chance, I believe sequence is also versus.
But I could easily kind of believe that there's some computational nature to the universe, and you could write some Turing machine that simulates me flipping the coin each time, or something like that, and that maybe it turns out to be like some sort of weird computable sequence. And I feel
Yeah,
like
then the star law falls.
yeah,
If there's a computable pattern, then
Yeah, if there's
it falls outside law.
See, we're in Earth, right? That was something you said earlier on. There's no data we can look at to tell the difference between L and L star.
L and L star would be distinguished. But a world that is where the results are governed by some like how complex like will be very star.
But your point was that same sequence would come up just that way. When 50-50 every time and still get a sequence.
yeah, the limiting frequency would still be 50-50. I think. So I feel like, I don't know, I'm personally feel hesitant about accepting an L star law, and I was wondering like if you have.
Yeah, I think
justification.
metaphysics is hard. But here's an epistemology that's easier. So think about the choice of modal boundaries of which was the possible. This is omega L, the space of sequences compatible with L, and here is omega L star. Okay, I mean, I'm drawing this too large. But to commit to this law and to commit to this law is of the same epistemological flavor, in the sense that if I commit to L law, I'm denying this is the real boundary. If I commit to L star law, I'm denying L is a real boundary. I'm saying something about physical reality, about what's physically possible. That's of course beyond my current evidence, so there's theoretical arguments. But taking L star law is not more ambitious than taking L law. Because taking L law is not being agnostic about boundary in modal space. Does it make sense? So epistemologically, if you think about whether something is within our right to accept or not, we'll just say, okay, L star and L, do they fall on different sides or do they fall on the same side? So by this argument, I think there's a fundamental difference between accepting L star law and L law in terms of cumulative.
Also, in terms of the metaphysics, like you don't know what laws are, and so there's no good reason to think that our intuitions are going to be very much the guide to what kinds of laws are possible. And historically, they haven't. Science has gone in lots of directions we wouldn't have expected. So, I think I feel the pull of your feeling that that's a bit weird, but like, why should laws be according to what we consider to be weird or not weird?
Yeah, I also think more so there's something special about star. It exists, right? And that seems like a strong thing. But if I really embrace a standard chance law, I'm insisting the world is metaphysically in or standard chance law, even if outcomes alternate out to events. So I'm not sure that it's going to be a stronger kind of insistence. Here's another worry that I think is in the same ballpark. Somebody might say, why should algorithmic have anything to do with laws of nature, with the laws of physics? Why should computation, something completely different from physics, why should we expect a starlight show quantum mechanics? And I think part of that is fleshed out with what Eddy was saying up front in the presentation. The role of algorithmic randomness here is just to try to make sense of what we mean by pattern-free, unpredictable, no fair betting strategy. It doesn't come up because we're committed to some notion of computation in the part of physics. It's just an only tool we have available for making sense of what we believe about the physical world. That is, that our results will be distributed such and such frequency. And so that's the way I've gotten how the randomness gets involved in a plausible information.
Yeah, one related thought that is related to concern is that algorithmic randomness is perhaps our best worked out theory of randomness, of chance.
I think hands down it's our best. It's the only way I understand what's say that sequence is random. Somebody might say, oh no, what I mean by random is with probability P and independent distributed ID. But if you want to test for independent distributed frequency, you're going to have to give them a procedure. You're going to solve it. So in terms when try to get traction, even on what we mean by an IRA process, we have to start talking about prediction.
Right. But if there is, a better way to think about randomness, there's not much law of randomness, then I think we just defer to that.
Yeah.
And see what is best way to cache out randomness.
It'll be a different account.
There'll be different count.
But this account will still be
Right,
unlimited.
exactly.
Yeah, just sort of related to this conversation, I guess. I'm inclined to look at this proof and sort of add then given that all these forms of randomness are empirically equivalent and we can't tell the difference, whatever credences it's rational to set in the Marshall of randomness world must also be rational to set in our world because they'll look the same to us. Is there a reason you would or wouldn't give that argument? Like, are you willing to say that as an argument?
That's a good point. So we consider this argument, and there's like a transfer principle. Because if empirical equivalent up to some limitation, then you might transfer the same classification to other L star laws or even L laws.
Yeah.
The L star laws, I can see how that might go because the same proof would go apply. But for L laws, I'm not so sure. Even if L law is empirically distinct from L star law, I don't see what justifies the transfer principle. I can see that for practical purposes, it might be reasonable to rely on this because what if L law is really described by L star law? That is just accepting that L is better described by L star.
This an intuition that if you genuinely buy that there's no way we could possibly tell the difference between them, then you might think, how could it possibly be the case that it's rational to set different credences for these different laws? And then you might say, well, regardless of whether L star is right, in fact, this reasoning is still going to apply.
Yeah, I think we can pinpoint exactly the difference between L and L star law in the proof. That L star entails theta equals 0.5, but L law entails mu of L of theta equals 0.5 is 1. So it's measure one factor, it's a full space vector. And that's how the two proofs come apart. One will be circular, one will not be circular.
No, I mean, I appreciate that you can't do the proof with the L laws, but,
Right.
but given that there's the expectation that it's correctly the same, you might think that even though you can't do a proof for the L laws, it must be rational to have the same credences nonetheless.
I hope that's true, but I don't know how to justify that. The transfer principle. Yeah.
So we'll throw something in here, something that Eddy could have said. I'm going to say it for you. I don't know if I feel this way, but one of the things that Eddy certainly solves is to use solve. Right, they address the big bad bug, they address fitness, they give us a path to principle,
Yes.
and we're giving all of that up. Now you might say, but that's not really evidential for binding star law. It's good conceptual.
Yes.
Star law. And so I think there's an argument on conceptual terms.
I mean, yeah, I do like star laws. I want to keep them. I was wondering if it gives a way of responding to concerns like the ones that have been raised. How do we really know it's star laws? Well, maybe in some sense it doesn't matter for this particular reason.
I think I'm just, in my personal metaphysics, I feel like there's something inherently computational about the universe. And that's does not work with an L star law.
Yeah, this is
Yeah.
and it is just patience on algorithms. That's what I mean. Then no star law.
I was wondering if you could give some hints about the third point, how this might connect to quantum mechanics and statistical mechanics. It seems to be some way to, if it does, then entropy and the way, I mean, whether you think we're in a deterministic world or not, will have a big impact.
Yeah, it's a good question. So we're still working on this part, but maybe I can give some hints on how this may be connected. So in a theory called, so there are different interpretation quantum mechanics, different ontologies and different laws. One of them is called Bowman mechanics. Another is called averaging quantum mechanics. On both interpretations, there are these wave functions that spread over many possibilities. And there are maverick branches of the wave functions. They're in some sense analogous, but also different from the every sequence is considered. One way to transfer talk about L-star law to Bohm's theory is to think about when you have a wave function psi, and you have some initial configuration of the universe Q, guided by size evolution by precise law. There is a separate constraint called the quantum equilibrium distribution that says the position of particles are random with respect to psi. So you can induce a randomness constraint using psi and much love randomness on position of particles, then we're good to go. For the system mechanical case, there is another kind of theory called, a past hypothesis kind of theory, where you have initial conditions, say x0 or wave function 0 in some particular region called M0, the initial network, and a particular mu0, initial measure of randomness for these configurations or quantum states. And that's also random. So if there's a way to connect the randomness here, much love randomness in this particular set, then we're good to go. Of course, there was the details, which are still working.
You also have anything to say about EQM, the last one? Everything quantum mechanics.
Yeah. So a lot is said about EQM, but Jeff, do you want to say something about?
No.
Okay.
No, I want to talk about Bohmian mechanics because it's easier for reasonable Kelvin outside. So this is another way to put the point Eddy just made. One of the nice things about the star law is that it gives us a way of saying what we mean by that distribution postulate. It's essential for Bohmian mechanics. Bohmian mechanics does not mean the right for predictions. You can put the complete initial configuration in wrong place. It only makes it if it's randomly placed relative to the wave function. But what does that mean? Del star law would say what in terms of the test that initial configuration says. So it gives us a concrete way to specify.
And there are various theorems in statistical mechanics, classical and quantum, that the flavor of, say, the laws of large numbers in probability theory, they're actually applications of laws of large numbers. There's concentration results and Chernow bound and so on. And those things give us the kind of randomness we need to play out this initial randomness into the histories of events that follow from the initial state. So those things are kind of the clues for how to connect this picture of L star. This way are designed for, say, experiments and coin tosses and so on, into a more realistic setting. You have just physical stuff and states that can sometimes connect.
Average quantum mechanics thing on this. Seems like L star limits macro growth. Is that basically what you would conclude? You try to develop this relative computer?
I'm not sure, actually. I'm not sure if you want to eliminate the network worlds or use other ways to building randomness into the everything picture.
Yeah, I don't see how it would still be a written one. Sorry, I would take a written one mechanics system. Yeah, so we're stuck with.
Yeah, but so how would you apply this to it? Do you have other ideas then? What else are
It's going to have to show up. It's going to have to show up in how extractable. In particular, forward with.
So probability to see less than one branch.
Yeah, so I'm sitting here and I'm getting ready to experiment. So we generate a split with one random state here. And I want to assign forward to give mutually in some sense. But in some sense, I'm running both of them. But I want to make something around that. The story about how that's going to go, that's which I've really talked to. And it's at that point with star law. show up. And so how the star lot stuff interacts with the Iridian quantum mechanics. It doesn't show up at the level of describing what happens. So they have to show up in the context of the kind of forward-looking beliefs you have concerning your expectations regarding future outcomes in the limit.
But we end up with a belief that never was impossible, but you iterate the negative self.
Yeah, so somebody might end up with a personal expectation rules out as being worlds that don't deserve any consideration. And they're going to sleep at night. They know the unitary dynamics, they know the real, but presumably they sleep at night.
Does that violate your principles?
So I don't know. I haven't even thought about what principle.
Maybe I'm asking you to test that too far ahead.
Yeah, but the reason I didn't want to address the Iridian case is that the story really is going to turn upon what kind of
It may not be objective probabilities in the end. If you have self-locating probabilities or some centered cancers, then it becomes a hybrid thing. So even then, which principle should we even use becomes open question. Thanks.
We were talking about advantages of the approach. I was just confused by one of them, which was for the non-Humeans. What the advantage for them was. You mentioned the move to L star gives you sort of the notion of constraint that a non-Humean wants. Although I would have thought even with L, you get constraints, for example, with probability, ruling out possible histories.
But L laws don't rule out those histories. So, different L laws are compatible with the same counter space. And the zero probability events are still possible on the model space.
Okay, that's part of what you mean by the L laws there.
That's
Zero
right.
probability ones are still possible.
Yeah, the probability zero events are all possible, and all of them, so omega L.5 equals to omega L.67 equals to the counter space. So they all have the same set of possibilities. Whereas the star law is carving out into different chunks.
I have a question. So on one of your slides, Eddie, you had transcendental Bayesian. Is this a real thing? I like it.
Maybe we should call it Kantian Bayesianism.
Yeah. So you have to know that I like that.
Yeah.
Is there anything like that in the literature? So this would be accepting exchangeability as a precondition for
Yeah, it's a good question. What is the precondition? Is it a rationality requirement? Or?
It's not going to be, right? It can be a good base to exchange providers.
So it's softer than the norms of rationality, but stronger than mere probability coherence.
Yeah. With respect to a particular process, I kind of think of myself as I just have to have exchangeable reads with respect to the process.
Yeah.
Not as a precondition for it. I just find myself with them. And if I find myself with them and I find myself committed to star with them, then I find myself committed to short and medium run credences.
Right.
Or all natural ways with our practice. If I don't find myself with exchangeable, then there's the puzzle of how I'm going to bootstrap up to that.
Yeah.
So I think this is a good thing for us to think of.
Yeah, I should also mention I didn't talk about other structures, other symmetries. It was purely the proof based on exchangeable symmetries. But you can imagine a mixture of different symmetries, some Markov dependencies, some other dependencies, and you get a similar kind of proof, conditionally on stuff. And that doesn't require further principles follow from conditionalization. So that's a generalization that is possible given the framework. So you take a credence that's spread of W1 something plus W2 something, conditional on particular L star wall, you get the right symmetries for the L star wall.
It's 5:30, so we could cut it off there. Thanks.